This video begins Chapter 7 on sampling distributions and Section 7.1 on what is a sampling distribution. So before we can get started, there's several definitions that you need to know. So the first one is parameter. So a parameter is a number that describes some characteristic of the population. It's important that you know that a parameter has to do with a population. So it might be helpful for you to think about P for parameter, P for population. In practice, the value of a parameter is usually unknown because we cannot examine the entire population. The second is statistic. So a statistic is a number that describes some characteristic of a sample. So it might be helpful for you to think about statistic and being with a sample. So both of those start with S, just like parameter and population. The value cannot be or can be computed directly from the sample data. We often use a statistic to estimate an unknown parameter. So a lot of times we'll use a statistic to find a parameter. The next one is sampling variability. So the value of a statistic varies in repeated random sampling with sampling variability. And the last one is sampling distribution, which is what this whole section is going to be pretty much about, and really this whole entire chapter. So the distribution of values taken by the statistic in all possible samples of the same size from the same population. So to get started, we're going to be looking at a couple of different examples so that you can see the difference in a parameter and a statistic. So your directions are for each boldface number in questions 1 and 2. Basically, those are going to represent either a parameter or a statistic. In each case, state whether or which it is and use the appropriate notation to describe the number. So on number 1, it says on Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. So we know that we're going to be finding a parameter and we're going to be finding a statistic. And so our two bolded numbers that they give us in our problem are 20 and 19.6. So one of them is a parameter, one of them is a statistic. So remember that parameter starts with a P, just like population. So parameter and population are going to go hand in hand. Now, whenever you find a statistic or a parameter, you are finding the mean. But remember that we represent mean two different ways depending on whether we're talking about a population, like we would be with a parameter, or whether we're talking about a sample, like we would be with a statistic. So remember that whenever you're talking about the mean of a population, you would use mu. And when you're talking about the mean for a statistic or a sample, you're going to be talking about X bar. So mu is for population, X bar is for sample. We know that parameter is going to be for population, so we use mu for population and parameter, and X bar for statistic and sample. All right, so looking in there, we have that the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces. So this kind of has to do with our population, our entire population. It goes on to say, and this might be more helpful to you, quality control inspectors sampled, so there's the word sample right there, 50 bottles at random from the day's production. These bottles, so the 50 bottles that were sampled, contained an average of 19.6. So because these bottles were sampled from the entire population, the 19.6 is going to represent our average for our statistic or our sample, which means that the 20 ounces of iced tea at the beginning of the problem are going to have to do with the population. So the 20 is in ounces of iced tea, and the 19.6 is also in ounces of iced tea. Number 2. On a New York to Denver flight, 8% of the 125 passengers were selected for a random security screening before boarding. According to the Transportation Security Administration, 10% of the passengers at this airport are chosen for random screening. So we know we're going to be finding a parameter and also a statistic. We know that with both of these, we're going to be finding a mean, but the way that we represent or notate the mean for each of these is going to be different. So the notation for a parameter, because parameter has to do with the population, is going to be mu. And the notation for a statistic, because it has to do with a sample, is going to be x bar. So the mean for the parameter has to do with the mean of the population. So our mean for the population is going to be the 10% of the passengers at this airport. So 0.10. The x bar, which is going to have to do with the sample, so the people that were selected were the 125 passengers, and we know that 8% of those were selected. So 8% were selected or sampled, and so that turns into 0.08. All right, for the next example, we're going to talk about simulating a sampling distribution. So we use Fathom software. Fathom is a special software that's used for statistics. I'm working on getting you all a copy of Fathom because it's really great. It's really great for building tables and graphs and that kind of thing. And a lot of the graphs that you will see with Fathom, or the graphs that you can build with Fathom, are pretty similar to what you would see on the AP exam. So this is an example of a graph that was built with Fathom. And again, I'm trying to get you all a copy of that software so that we can use it in class and you become more familiar with it. So anyway, we use Fathom software to simulate choosing 500 simple random samples of size n equals 20 from a population of 200 chips, 100 red, and 100 blue. Figure 7.2, which is this figure here, is a dot plot of the values of p hat. So it's kind of hard for you to see this right here, but this symbol right here is p hat. And the reason we call it p hat is because it looks like the p is wearing a hat. I know it's really, really like groundbreaking, really creative with the name, but that is the actual terminology for it. So p hat is the sample proportion of red chips from the 500 samples. So A says, is this sampling distribution of p hat? So whenever you look at this graph is not the sampling distribution of p hat because it doesn't show the values of the statistic in all possible samples. So remember that p hat is the sample proportion of red chips, and this graph here shows the sample proportion of red chips, but it is not the sampling distribution of p hat because it doesn't show the values of the statistics in all the possible samples. So all the possible samples being the red and also the blue. B, describe the distribution. Are there any obvious outliers? So remember, to describe the distribution, you're going to talk about the shape, and you're going to talk about the outliers, and you're going to talk about the center. And the spread. So remember that when we were talking about looking at the distribution and talking about the general things that we see about it, we called this SOX, so shape, outlier, center, and spread. So let's start with shape. So when we look at the shape, we see that it kind of has this shape, which means that it is symmetric. We can tell that it's unimodal, which means it just has one peak. And we can also see that it's somewhat bell-shaped. when we talk about outliers, when we look here at our graph, we kind of see that everything is pretty close together except for this one right here. So there's like a gap here, and as you can see on this side, there's not a gap at all. So everything's just kind of continues on and on this side. But over here, we see this kind of gap right here, which means that there's possibly an outlier there at 0.15. So we see that we have one sample with p hat equal to 0.15 that stands out. And the reason it stands out is because it's kind of over here by itself. It's kind of got this little gap shape in between that point and the other points over at 2.5. So even though it's not terribly far away, it's still further away than all the other points. And we don't have any other points that are far away like that. All right, the next thing we're going to talk about is the center. And so it appears that the center of our graph is probably right about here where we have our peak. And so the center, we would say, is around 0.5. And so to talk about the spread you can see here shows that the values of p hat are mostly between 2.5, or really that's 0.25, and 0.75. Next thing we have to do for C is suppose your teacher prepares a bag with 200 chips and claims that half of them are red. A classmate takes a simple random sample of 20 chips, 17 of them are red. What would you conclude about your teacher's claim, and explain? All right, so if you think about it, your p hat for this scenario would be 17 out of 20. And so if you were to do 17 out of 20, that would give you 0.85. And so it's pretty unlikely that you would obtain a simple random sample of 20 chips in which p hat, which is the sample proportion, would be equal to 17 out of 20, or 0.85% of the population of 200 chips, half of which are red. In fact, the values of p hat this large never occurred in 500 simulated samples. This student's results give strong evidence against the teacher's claim. So because this number is so high, we wouldn't expect it to be that high, because we would expect it to be about 0.50, because we said that there's 200 chips, half of them are red. So this is incredibly high if we're thinking about half of the 200 chips being red. So we would say that this gives evidence against the teacher's claim, and we would say it seems doubtful that the bag actually contains half red chips. It seems like there's probably more red chips than there are blue chips if we come out to have a sample distribution of 0.85. So next we're going to talk about a population distribution. So with a population distribution, that is the values of the variable for all individuals in the population. So we're going to look at an example having to do with, of course, M&Ms. So Mars Incorporated says that the mix of colors in the M&M's milk chocolate candies is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. Assume that the company's claim is true. We want to examine the proportion of orange M&Ms in repeated random samples of 50 candies. Number 1 says graph the population distribution, identify the individuals, the variables, and the parameter of interest. So for number 1, we would say that the individuals are M&M candies. The variables, or the variable, is the color. And the parameter of interest is the proportion of orange candies. Alright, so it also asks us to graph the population distribution. So basically what you would do is using the percentages that they gave you here, you would create a bar graph. So based on our percentages that they give here, it's probably a good idea to go up by 5% each time. So we would start obviously at 0. This would be 5%, 10%, 15%, 20%, and then 25. And so, of course, across the bottom, we would have each of our colors. So we'll start with blue. Blue is 24%, so almost all the way to the top. Then we have orange. And orange was at 20%, so not quite all the way to the top, but pretty close. Next, we have 16% for green. Then 14%, so a little bit below that. And that was yellow. And then a little bit below that is going to be red. And beside that, exactly, is going to be brown. Alright, so for number 2, it says imagine taking an SRS of 50 M&Ms, make a graph showing a possible distribution of the sample data, give the value of the appropriate statistic for this sample. Alright, so you know that you have 50 M&Ms, and you know that in that sample of 50 M&Ms, 20% of them should be orange. So to get an actual number of M&Ms that should be orange, we would take this entire sample, 50, and we would multiply it by the probability that one is orange to the 0.20, and whenever we do that, we would get 10. So that means that we should expect about 20 candies to be orange. Or 10 candies to be orange, excuse me. Alright, so make a graph showing a possible distribution of this sample data. Give the value of the appropriate statistic for this sample. Alright, so because we are expecting there to be about 10 candies that are orange, our p hat would be 10 out of 50, which turns out to be 0.20. All right, for 3, which of these graphs that follow could be the approximate sampling distribution of the statistic? Explain your choice. So for number 3, the middle graph looks like it could be an approximate sampling distribution of p hat. The statistic measures the proportion of oranges in the sample of M&M chocolate candies, assuming that the company is correct. 20% of the M&Ms are orange, so the center of the distribution of p hat should be at approximately 0.20. So if we look at each of these, the p hat is going to be the one that we're really worried about, so we're down to either this one or this one, and we should be looking for 0.20 to be like the peak of our graph, because we are talking about orange candies. So the middle graph would be the one that could be the approximate sampling distribution of the statistics, because the p hat should be approximately at 0.20. So the reason that the other two are wrong, so the first one shows the distribution of the colors for one sample rather than the distribution of p hat for many samples. So this is kind of just showing like each color and not like a repeated sampling like the other two do. The third graph is centered at the wrong spot, so it's not centered at the 0.20 like we needed it to be because of our p hat. So we can eliminate that one. Unbiased estimator. So an unbiased estimator is a statistic used to estimate a parameter if it's unbiased, if the mean of its sampling distribution is equal to the true value of the parameter being estimated. The variability of a statistic is described by the spread of a sampling distribution. The spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of a sampling distribution does not depend on the size of the population as long as the population is at least 10 times larger than the sample. So check your understanding to kind of make sure that you have grasped all of that information and really some examples so that you can see how these work. Number 1 says the histogram above left shows the intervals in minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions during a particular month. From this population, the median is 75 minutes, so we can see that from the information there. We use Fathom software to take 500 simple random samples of size 10 from the population. The 500 values of the sample median are displayed in the histogram above right. So, the 500 values of sample median are here. The mean of the 500 sample median values is 73.5. Number 1 asks, is the sample median an unbiased estimator of the population median? Justify your answer. So on number 1, the median does not appear to be an unbiased estimator of the population median. The mean of the 500 sample medians is 73.5, whereas the median of the population is 75. So, no. The median does not appear to be an unbiased estimator because the mean of the 500 sample medians, which is this one right here, is 73.5. Whereas in the first histogram that we had. The median is 75. So because it's off, even though it's off by just a little bit, we still would say that it is not an unbiased estimator. 2 says, suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? Justify your answer. All right, so to kind of go backwards a little bit, larger samples give smaller spread, like we talked about here when we talked about the variability of a statistic. So, what we would say for that, because it is asking us about the spread of the distribution, we would say that it would be smaller. So because we're increasing the sample size from 10 to 20, we will decrease the spread of the sampling distribution. So you could say the spread will be smaller because we are increasing the sample size from 10 to 20. Three asks us to describe the shape of the sampling distribution. Explain what this means in terms of overestimating or underestimating the population median. So, basically, remember that this is the graph of the sampling distribution. We are just describing what that shape looks like. And so if we look at that shape and we kind of sketch out what it looks like, it appears to look like this, which looks like it's skewed a little bit to the left. So, we would say it's skewed to the left. And what that means is, in general, it underestimates the population median will be greater than overestimates. So to kind of sum everything up all together, this is kind of an illustration of bias, variability, and shape. So we can think of the true value of the population parameter as a bullseye on a target, and of the sample statistic as an arrow fired at the target. So all of our little dots would represent the bias or the sample statistic, like where it actually hits. And we could think about the location of it as being the population parameter. So both bias and variability describe what happens when we take many shots at the target. Bias means that our aim is off. So if we see, like in this example, that we're off from where center should be, then that would mean that our bias was kind of high. Our sample values do not center on the population value if our bias is high. High variability means that repeated shots are widely scattered on the target. So high variability would be like we're all over the place. Repeated samples do not give very similar results. So even though we're doing this a lot of different times, we're not exactly having the same results every time, so it's kind of spread out all over the place. So the figures over here, 7.8, shows a target illustration of the two types of error. So the first one, we see that we're kind of off center here, which means that our bias is high, but we see that we're all kind of grouped together, which means that we have low variability. So we're repeating the sample over and over and over again, and we're getting the same result, but the way maybe that we are we're going about getting that information is a little bit biased. In the second example here, we see that we're kind of closer to the center, especially than we were here, so our bias is low, but our shots are kind of spread out all over the place, so our variability is pretty high, which means we're repeating it over and over again, but we're kind of getting different results every time. On this example, we see that everything is kind of spread out, And we're also way off of the target, which means that our bias is high and we also have high variability. And the last example is the kind of ideal situation. So everything is centered in the middle, which means we have no bias, and everything is all kind of grouped together, which means that the variability is low, so we're repeating the same process over and over again and getting the same results.